Okay, hello everybody. What we're going to have a look at today is moments of forces, and for this we need a bit of a seesaw arrangement, something you might find when you were a kid down at the playground. We have a piece of wood here, and you can imagine one person on this side and the other person on this side, and unless they actually weigh exactly the same, the seesaw will go in one direction. When the seesaw is left alone, the wood, in this case piece of wood, is resting, and we call that equilibrium. So when all the forces in the system are equal and there's no movement in anything, it's called equilibrium. So this tin of tuna, for example, it's not in equilibrium at the moment because I'm moving it around. As soon as I drop it on the table, it stops and it's in equilibrium because the force on the tin of tuna pressing down onto the table is the same as the force of the table pushing up, so it's in equilibrium. Right, so you can demonstrate this with this arrangement here. If I say one of these tins weighs about 2 newtons, it's just under 2 newtons, but say 2 newtons each. If I put that there, it tilts that way. If I get another tin of tuna, the same force, and put it that way, it balances out. And one thing you need to notice is the two forces are the same, but equally these two distances are the same. We'd normally measure the distance to the centre of the object. In this case it's about 180 mil, and in this case it's pretty much the same. Now, what you need to be able to understand is if I put another tin of tuna on this side, it tilts that way. And the only way I can get it back into equilibrium is to either put another tin of tuna on this side to balance it out, or alternatively I can stick with my original tin of tuna and move it right to the end. I don't know whether this is going to work or not. It might work. Oh, yes, it does. That's alright. So you can see the tin of tuna is right at the other end of the scale. I don't know whether you can see that on the camera. There's the tin of tuna there, and there's 2 tins of tuna there, and you'll see that that distance is much longer than that distance. And we call these forces about a fulcrum. This is what we call a fulcrum. These forces are called moments. So a moment is a force that's acting on a fulcrum like that. And you can find that situation in frameworks like electricity pylons. You could find the situation in spanners, wrenches, levers, etc. And we'll come on to that a little bit later. So what we're going to talk about is the forces and the distance. The moment is known as the force, in this case say 2 newtons, times the distance. In this case it's about 150 mil each side. And for equilibrium to occur, the distance times the force on one side must equal the distance times the force on the other side. So it's force times distance on each side must be equal for equilibrium to be maintained. So if I had 2 tins of tuna there, to get it balanced, I can move that out to about there, which is about twice the distance. So if I measure that distance, it's 140 mil. If I measure that distance, it's about nearly 280. It's a bit crude this, because this is a flat piece here. I'm trying to get it to show itself balanced, but I think that's probably about right there. Let's get a bit more accurate. So that distance is 150, and that's virtually 300. So you've got twice the distance there on one side, the 2 tins of tuna. Okay. So we need to be able to calculate that somehow. So one way we can do that is to draw our little diagram.